So if we take a look at this, you need to label the linear axis over here, and what you kind of want to do is spread things out. For example, I could make this minus -10 and this -20, but everything would be kind of squished together. So I've let each major division here be equal to 5 dB, and I've gone above 0 to +5, and with our relative approach to this, V out over V in, we can never ever get above 0 dB. So this can be kind of a confusing graph over here, and what I've elected to do when I made these points is these major divisions between the 5 dB increments I labeled as, in this case, -12.5 and -7.5 and -2.5 to help me keep track of this, because it is kind of hard to go vertically and then horizontally when you're dealing with lines that are that close together. Now what's super important, and what we need to do, is look at the frequency axis here along the top. Is we see a 1, a 2, a 3, and then over here a 1, a 2, a 3, and over here a 1. And we keep doing that for 5 cycles, and the distance between these is the same. Now, if you turn this paper upside down, it'll be 198, and that is completely wrong. So before you even start this, you have to look at the actual labeling of the graph to make sure that it's ascending. And sometimes this will be on the bottom. So you can't assume it's always going to be on the top. You have to look at it. If you get it wrong, your whole plot's completely wrong. So what I've done is I've used the point by point here, and this comes off the calculator I spoke to, and all these little dots are making up the point by point, and then the critical frequency is down 3 dB. So this is 2.5 dB, and then I'm down one little mark from that, which would be -3, and that occurs at 100 Hertz. Now, how do you label this? Well, where is your critical frequency? Maybe it's 1 megahertz or 10 megahertz. And if this were 10 megahertz, then this would be 1 megahertz, and this would be 100,000, and this would be 100 megahertz. So you can adapt this graph to any critical frequency that you need, and that's really pretty cool. So we're kind of down at the low end here at 100 Hertz, and the next step after I get this labeled and understand this and get my point by point in carefully, and it's an error-prone thing with the point by point. If you get an outlier, one point that's really not lining up right, you need to re-examine the value of that, and it's probably that you didn't get it on the graph correctly. It's a very easy thing to do. So I've identified my critical frequency right here, and then I go vertically 3 dB. Very important. See a lot of people that come over here and then go up and make a point. No, it's vertically above your critical frequency and make a point. Second point is a reference value, a high frequency in this case, and then the Bode plot would simply be placing a ruler between these 2 points and drawing a straight line to this point. Second line, this is going to be a diagonal asymptote, would be to locate the -20 point that's a factor of 10 lower. So this would be 1 decade, and here we're 100 Hertz at critical frequency, and this is a high pass filter. As you can see, the high frequencies basically are unattenuated somewhat, or mostly. So I'm going to come over to 1/10 of that, 10 Hertz, and go down 20 dB and put a mark there. So the second part of my Bode plot would be placing the ruler between our reference up here at 0 dB and -20 dB and drawing a straight line. So that is what the Bode plot for the circuit would look like. Now, this wraps up an awful lot of detail that we talked before, which probably didn't connect well to what we ended up with. So it might not be a bad idea to go back and kind of look things over and make sure that you understand what's going on, because it's likely you'll be asked to make a Bode plot. And if it says it wants point by point and the Bode plot, that means that you're making 2 plots, not 1. So that'll basically conclude Bode plots using a high-pass filter as a reference. And thank you for watching.